That's what I do. And yeah, so then let's start. First, I would like to introduce the objects which we are studying in. Namely, on the symplectic side, I want to recall a symplectic manifold always admits an almost complex structure. And so that when we twist the second factor of the symplectic form with this almost complex structure, we have a Riemannian matrix. And the space of such almost complex structures is contractible. And so when we pick such an almost complex structure, we can see the tangent bundle as a complex vector bundle over the manifold. And so we can define Chern classes for the symplectic manifold as we do here. So the first Chern class of a symplectic manifold is the first Chern class of the tangent bundle together with an almost complex structure which is compatible with the symplectic form. And so I want to define the next symplectic Fano manifolds. So in this talk, a symplectic Fano manifold is a compact symplectic manifold, such that when we are considered the first Chern class, then the first Chern class is equal to the class given by the symplectic form in the second DRAM group. Okay. On the algebraic side, we are consider Fano varieties. Fano variety is a smooth complex variety, such that its anti-canonical line bundle, which is the dual to the dual tangent bundle, the determinanten line bundle to the dual, is ample. And this means the following: we can find a holomorphic embedding of this variety into some projective space, and when we in such a way, and when we pull back the canonical line bundle, which I denoted by OI, via this holomorphic embedding, then this is the tensor power for some k of the anti-canonical line bundle. And what you can observe in this case is, like, because of the naturality of the Chern classes, we have the following: that when we are endowed our variety X with the pullback of the Swabini study, the symplectic form on the projective space, then we can rescale this form with a positive multiple, with a positive number, such that when we consider X together with the form R times the pullback of the Fubini body circle, that this is a symplectic Fano manifold. So this means we can loosely saying that a Fano variety is automatically a symplectic Fano manifold. And so this leads to the following questions. Namely, the question is, when is a symplectic Fano manifold diffeomorphic to a Fano variety? And how to say, in real dimension 4 and 2, this is always true. I mean, in dimension 2, it's very easy to show. In dimension 4, this result goes back to work of McDuff, Groovemore, and Taubes. And in dimension 12, also for dimension greater than 12, not always, because Fano and Panov, they give counterexamples of symplectic Fano manifolds which are not diffeomorphic to a Fano variety. And in the dimension in between, it's still open, it's a little known, but not that much. And actually, I was, how to say, more interested in the case when, about this question in the case when the manifold, the symplectic manifold, is endowed with a Hamiltonian symmetry. And so, also for Hamiltonian T-spaces. And so we are considering compact symplectic manifolds endowed with an effective and Hamiltonian action and with moment map. And yeah, so we call such a quadruple complexity K-space. And the complexity of the action is the integer given by the dimension, by half of the dimension of the manifold, n, minus the dimension of the torus. And it's well known because we're assuming that the action is effective, and that this complexity is always non-negative, and how to say, yeah, okay, good, then. I wanted to say something about the complexity zero case. So the point is, so you can assume you have a complexity zero space. Then it is well known that its moment map image, the moment map image of such a space, is a smooth polytope. This is well known because it's a complexity zero space by Desarn's work. But this polytope satisfies also a second nice condition, namely it is a reflexive polytope. And in particular, we have a complete classification, like also in the same case like Desarn, we have like that, how to say, complexity zero spaces, which are satisfying that the first Chern class is equal to the class given by the symplectic form, are classified by smooth and reflexive polytopes. And I also wanted to mention something about the reflexive polytopes. Namely, it is clear that in any dimension, there exist just finitely many of such guys. So in particular, we have in any dimension just finitely many complexity zero spaces, which are satisfying this first Chern class, that the first Chern class is equal to the class given by the symplectic form. And yeah, how to say, in general, I was working on the cases where the complexity of the space is not equal to 0, and it's equal to 1. So how to say, we are failing by one dimension to be a complexity 0. Yeah, and I made some progresses together with Silvia Sabatini and Daniele Seppe. And yeah, so we was concentrating first on the case that we was considering Tor complexity 1 spaces. And actually, I want to remember quite what this means. Tor complexity means whenever you have a point in your moment map image, then the pre-image of this is not a point, it is a topological surface. It's a topological surface for all x, and these spaces right, sorry, the reduced spaces are symplectic surface, right? And so we classified them by the following. So we figure it out as a first point that when you have a complexity 1 space with that the first Chern class is equal to the class given by the symplectic form, then the moment map image of this space is again a smooth and reflexive polytope. But here I want to say for sure this does not give you the space back. But then from this out, we're starting to asking ourselves, so what is if I have a smooth reflexive polytope? How many complexity 1 spaces can I obtain which have this moment map image? And so we worked on this question, and with this we used really the important work by Yael and Susan for the Tor complexity 1 spaces, because they classified them. In particular, they gave a list of invariants which determines these spaces up to isomorphism. And so we was able, how to say, compute for any smooth reflexive polytope a possible data which can happen, finitely many for any. And how to say, we realized them in the fact that we're saying, these data are coming from a complexity 0, 1. In particular, so this classification result, I mean, in this classification result is how to say contained. The result is that when you have a Tor complexity 1 space whose first Chern class is equal to the class given by the symplectic form, then the T action extends to a Hamiltonian complexity 0 action. And so as a corollary, because we know for the complexity 0 action, we know it, we have that whenever we have a Tor complexity 1 space with the which satisfy that the first Chern class is equal to the class given by the symplectic form, then M must be diffeomorphic to Fano Varieties. Okay. And yeah, so this is the, how to say, the classification for the Tor spaces. If we're leaving the Tor world, the point is we have so far not a complete classification result for not so far. And it's even harder to compute all the invariants which are needed. So actually, if we would have the how to say.
The details
And so I was then with Liat, who was concentrating again on this question, but not for the core case, and in low dimension. And the lowest dimension where it's interesting is dimension 6. And yeah, so the idea was with Liat, so we gave a complete classification of, also we was, how to say, we was considering dimension 6, and we first was considering GKM graphs, as a GKM scales. And as you know, here in the audience, I think many people know the GKM case. When you have a GKM action, you have naturally a graph of this action, a graph associated to the action. And with Liat, we gave a complete classification of this GKM graphs in dimension 6 for complexity 1 spaces with the C1. And how to say, this classification results relies strongly on the work of Godinho and Sabatini, because they gave us results so that actually this classification result is, how to say, a computer proof. So we proved this with the computer based on Godinho's and Sabatini's work. And as a result of this classification result, we have that whenever you have a GKM complexity 1 space such that the first Charton class is equal to the class given by the symplectic form, then the manifold is again diffeomorphic to a Fano variety. And I want to say something about the proofs here, because this is something which has to do with complexity 1. Namely, when you have this complexity 1 action, then you know that the GKM graph determines the equivariant and the ordinary cohomology ring. And here I have to be careful, also in particular, the ones with Z coefficient, with integer coefficient. I mean, this is important. And so we have, how to say, when we have an isomorphism between the GKM graphs of such spaces, then we know that this induces an isomorphism between the cohomology rings, and which maps the first Charton class, which maps the Charton classes of the one to the other one. And so with this, we are using a very classical result by Walyub and Zuber for certain 6 manifolds, which implies that under this consideration, these spaces are diffeomorphic. Yeah. And yeah, and I think so, yeah, maybe then I'm almost done, because I think so in the future, I would like to work with Liat. We want to extend this in dimension 6. Which seems so far good that we can use the techniques which we use for the GKM space, for the GKM case, also when we have only isolated fixed points, and for the case that we have maybe fixed surfaces, but we are not in the tall cases, then
there's still a complexity 1.
Yeah, there's the complexity 1. Okay. Yeah, then I think then I'm done, and thank you.